In this lecture, we will consider a number of analytic properties of the dynamic model, a few extension, inclusion of extra term in the dynamics, and then a few examples of uses of the dynamic model in inverse and direct dynamics, and also related to trajectory planning. So first of all, consider the case in which the full dynamic model, which we rewrite here for reference, suppose that we are in a condition where this term is 0, and we will see when this happens, or approximately happens. And we are at 0 velocity, so this is also 0. So we are left only in a situation where we, let's say, start at rest, there's no gravity contribution, and we would like to see what happens if we apply some input torque. Suppose that here no dissipative term, so only, let's say, motor input torques. So we would like to see what happens when we apply a torque, what happens to the acceleration of the system. So which joint accelerate and which not. Okay. And we have already considered this question for some specific cases. Let's summarize here, and we will see that everything depends on the structure of the inertia matrix of the system. So let's start with the most simple case, a Cartesian robot. You can compute the kinetic energy of this robot. It's a 2R case, 2P case, sorry, planar 2P case. And the inertia is diagonal. I invite you to compute the elements of M11 and M22, the diagonal element. Now, it is clear here that if we accelerate, if we give a force to the first joint, only the first joint accelerates. If we give a force to the second joint, only the second joint accelerates. And this acceleration will be just the same for the same amount of applied force, because M11 and M22 are constant, and the fact that this matrix is diagonal shows no inertial coupling between the two joints. A slightly different case is the following one. Just skew a little bit, let's say by 30 degrees or non-zero angle, the second joint. Again, I invite you to determine the kinetic energy of the system and to find out, extract from there the inertia matrix, and find out that there is this diagonal coupling. Of course, the inertia matrix is positive definite, symmetric, but no longer diagonal, although it is constant. You know that in these two cases, the assumption that we start with 0 velocity is irrelevant, because as soon as the inertia matrix is constant, this is identically 0. But of course, we have to consider the fact that we are in the absence of gravity, for instance, on a horizontal plane. So here you see that if you give a force to the first link, there will be an acceleration on both links. The acceleration of the link at which we are applying the force will have the same sign of the applied force. Third case, we have already considered this one, the planar prismatic revolute joint. So now we are introducing a revolute joint in the picture. The inertia matrix we have derived, it's constant on the diagonal. There are off-diagonal terms which are a function of Q2. So the same situation happens as in the Cartesian skewed robot, but in fact this depends on the configuration that we start from, in particular on the value of the angle Q2. Q2 is the angle between the first link and the second link axis. The 2R robot that we have considered in the last lecture, same situation, but here we have still a dependence on Q2, on the first element of the inertia matrix. So this coupling is there, but also the effect of a torque now applied to the first joint, it will accelerate both joints, but the first joint, the acceleration of the first joint will depend also on the configuration Q2, which is not the case here. And if you extrapolate this type of information, I invite you to derive at least the inertia matrix for this articulated 3R robot in space, also known as elbow type manipulator, under some simplifying assumption on the location of the center of mass. You will find that you have this block diagonal structure. This part is pretty much similar to a 2R planar arm. In fact, is link 2 and link 3 of this structure, but mounted on a rotating joint. And there's an inertia term on position 1, 1, which says that the inertia seen at joint 1 depends on the configuration of the second and third link. So if the arm is stretched or is folded, is up or down, and so on. So you see that if you invert this matrix so that you can isolate Q double dot, so you have a Q double dot under these conditions equal m to the minus 1 of Q times U, and this matrix, because of this structure, will preserve the same type of inner block diagonal structure. So that if you apply force only to the first joint, only the first joint will accelerate. If you apply a force to the second or third joint, or a torque, only the second and third joint accelerate, the first joint will not react. And this is because of the simplifying assumption on the location of the center of mass, and so on and so on. So you can see that this inertial analysis of inertial coupling between the joints, constant, absent, or depending on the configuration, is a very informative aspect on the dynamics of the robot. Of course, if you have an initial value of joint velocity which is different from 0, the effect will be different because of the presence of the C of Q dot term. And of course, same for the presence of G. So let's do an analysis of when the gravity term is present, or better said, when we can neglect the presence of G of Q. So when we have a potential term due to gravity which is constant, since G of Q is the gradient of this, then the term G of Q will vanish. For instance, every time we move on a horizontal plane, or the single link move on parallel horizontal plane. So when we change the configuration, we don't change the individual UI, so potential energy of the single link, and therefore the total potential energy of the robot. Or if we move in remote space, for space application, we can consider that the acceleration of gravity G0, which is 9.81 at sea level, is negligible, and therefore this motion occurs without the presence of gravity. We have also seen made some consideration when the gravity term is 0 everywhere because of a special distribution of masses. We have seen if for instance, for the 2R planar robot under gravity, if the center of mass of the second link is located on the joint axis, and if the center of mass of the first link is located somewhere so that there's a balancing of the torque due to the presence of gravity, so that the G of Q zeroes out, then we have what we call static balance. Static balancing of the structure. We can place the robot under gravity in a given configuration at rest, and the robot will remain there without the need of a motor torque to compensate for gravity. Other way of compensating gravity while we are changing configuration can be implemented from a mechanical point of view. This is called often mechanical compensation. For instance, we can add a system of spring along the structure which generate an elastic force which compensates for different configuration Q the term G of Q. It's not at all a simple mechanical design, but this can be done. At least 90% or 95%, if not the whole force due to gravity, is compensated by this extra mechanical system of springs. Another way of doing this, and we will analyze the structure, is when we have closed kinematic chains. In fact, in the presence of a closed kinematic chain, we can still apply the Lagrange formulation of dynamics and do a number of consideration on distribution of masses, which will simplify the structure. And this is quite relevant. So that we will see this in a moment. The next general consideration that we can make is on bounding the intensity, the norm of these different dynamic terms. For instance, in general, we can prove that the norm of the inertia matrix, pay attention, this is a norm of a matrix. We will say a few remarks now on the blackboard, but it's lower bounded by K0, so it never goes to 0, and this is because the inertia matrix, in fact, is positive definite for any Q, but it's also upper bounded. In general, it's upper bounded by a constant, K1, and by another constant and a third constant, which depends on the norm of Q and Q square, on the square of the norm of Q, because in general, we have to deal with prismatic joint as well. So if the prismatic joint extends, in fact, the inertia will increase, but at most increases in a quadratic way with respect to the norm of Q, if we don't consider any bounds. So this is a really nominal analysis. In practice, we will always have joints, prismatic joints, which have a limited range, while revolute joints may not have any limitation of range. Same story can be said for the any factorization of the Coriolis and centrifugal term. Remember that Coriolis and centrifugal terms are quadratic in Q dot. If we factor out one velocity, we have a matrix S which has a linear dependence on Q dot, so that the norm of this matrix can be bounded by the norm of the velocity that we're having, and again, a factor which may grow linearly with the norm of Q if we have prismatic joints which have no ideal limitation in joint range. And same story for the gravity vector itself. In fact, also for the gradient of the gravity vector that we will, this is a condition that we will use later when designing control laws. Now, if the robot has only revolute joint, things simplify. In fact, this is the most interesting case. So the Q K2, K3, K5, and K7 constants are positive constants can be set to 0. And we can say that the norm of the inertia matrix is lower bounded and upper bounded by a constant, which means that also the inverse of this matrix will be bounded by the inverse of this constant. The matrix S is upper bounded by a constant times the norm of the joint velocity. This may increase arbitrarily large in principle. And the norm of the gravity vector is always upper bounded by a constant. And the same is true if you have prismatic joints, but these prismatic joints have a limitation. Then this limitation applies, of course, for different values of the constant. So I should note here at this point that we are using this notation of norms indifferently for matrices or vectors. In fact, this norm of Q is a norm of a vector. This norm on G of Q is a norm of a vector. But the norm on S and M are matrix norms. So which norm are we using? So if we have an X in Rn, there's a class of P norms, okay, and the most famous one is when P is equal to 2, and we have the norm of a vector, P norm 2 of a vector is the standard Euclidean norm. So the sum of the square of the n component of the vector, and then the square root of this. This is the standard Euclidean norm. You have other norm when p is equal to 1 or when p is equal to infinity, so you're summing, in fact, so this is like the generalization is the pth root, here is the square root of the sum of the pth power so which boils down in being the maximum of the absolute values and other situation like this. So, but we will mostly work with this. What about a matrix A, which is, let's say, an n by n matrix? How do we define the norm of A? Well, in fact, we define the norm as an induced one from the norm that we are using for the vectors. In fact, the definition of A as operator is the superior of this operation. So you take a vector x, you apply the matrix A as operator, so you obtain a new vector, and then you take the ratio of the norm of the obtained vector, which is the destination vector, with respect to the vector that you have used to start with. Of course, you consider only non-zero vector. And the superior of this is the definition of norm for a matrix. Of course, a norm should satisfy some properties. So, for instance, the norm is always non-negative, and 0 if the element is 0, so if the matrix is 0, if and only if, or if the vector x is 0. And you have a triangular inequality that applies both for norms of vectors and norms of matrices. And finally, if you apply this definition and you're considering 2 to the matrix A, when you apply this property, is also the maximum singular value of A, or, which is the same, the square root of the maximum eigenvalue of A transpose. Okay, so you can compute this. So when we are saying that, for instance, this matrix has norm bounded above by K1, we mean that we are considering the product of M times M transpose, so that we are considering a symmetric matrix, but in fact M is already a symmetric matrix, but this is true in general. We take the maximum of the eigenvalues, which for symmetric matrices are all real, and then we take the square root of this. While when we are saying that we have a norm of Q dot square, of course we are considering the norm of the square root of the components of the velocity squared. Okay, so this is a kind of a remind on vector and matrix norms, and these properties holds in general. And we will see that we will use, for instance, this property, and also a property on the gradient of G, which is a matrix, being upper bounded by a constant in the case of revolute joints robots, or even including prismatic joint, but with a bound on their range. Okay, as I mentioned, there is a class of manipulators that we have not considered so far. We have only considered some special case for the kinematics, when we have closed kinematic loops. And what happens for the dynamics? We have made an implicit assumption that we have serial chain manipulators, so we exclude robots having loops like this, like in this industrial robot, or in this 2 direct drive research robot developed at MIT. Why do we introduce loops? Typically for displacing the location of the motors that are driving the joints. So the motors are not necessarily located on the joints, but may be located before. We will see what happened in that cases. But if we consider only now the mechanical structure in the presence of a kinematic closed chain, like in these parallelograms that are present in this robot, can we derive the dynamic model using the Lagrangian formulation? The answer is yes. So the serial assumption was just for simplification, for instance, for the recursive way in which we compute kinetic energy. These are 2 particular cases. Here we have a planar arm which has 2 motors, one below and one on top, moving an articulated closed kinematic chain. You see that this point is the same point as the point above, but on different planes. And this is another structure which has also a rotation at the base and the possibility of elevating the planar closed kinematic chain. So this is a 3 degree of freedom robot which contains a spatial 5-bar linkage, while here we have a planar 5-bar linkages. So let's consider as an example, this is quite important per se, but as an example of application of the Lagrange Euler equation for the dynamics in the case of this planar arm. And then we will consider not this situation, but the situation in which this planar arm is not on a horizontal plane, but is moving on a vertical plane, so that also gravity needs to be considered. So here is a schematics of this MIT direct drive arm. We will also see why the use of direct drive connection, so the fact that the motor is connected directly without a reduction gearing to the joint, which means that even at the low speed range, the motor should be able to deliver a high torque because there's no amplification by the reduction ratio, and also for control purposes, what happens then to the dynamic couplings. So we will see this explicitly for the resulting model. Let's introduce some generalized coordinate. No? The first step in a Lagrange modeling is introduce generalized coordinate in a number sufficient to describe the configuration of the manipulator, but not redundant. And here we see immediately that two angles that can be chosen because of this parallelogram structure. So these four bodies, 1, 2, 3, and 4, will move, but the two sides, L1 and L3, will remain always parallel, and 2 and 4, and we make a geometric assumption that this link length, L1, L2, L3, and L4, are subject to this geometric constraint, so that we can visualize quite clearly. Pay attention, the last link going from joint, the green joint close to the 3 label to the end effector is a single link. There's no bending at the blue joint. This is just a passive joint that allows rotation of the full link on that blue joint. The location of the center of mass of the 4 links, in fact, is arbitrary, is characterized, this center of masses are localized by this yellow circle with a cross through it. And there are also parametric quantities that specify where LC1, LC3, LC2, there's LC2 missing here, but where this center of mass are located. So with these two angles, Q1 and Q2, we can localize the configuration of the arm. In particular, if I'm giving an angle Q1 here, and there will be a motor that is activating this generalized coordinate, I know the orientation of link 1, but similarly, I know the orientation of link 3 because these remain always parallel. And similarly, if I'm moving with a motor this second link, so this 2-link base may move independently by 2 motors, then I know also the orientation of the link 4. And with respect to the horizontal axis x, if I have a Q2 here, I will have a Q2 minus pi there. And this is a geometric constraint. So I can use only 2 generalized coordinates to localize the configuration, to characterize the configuration of these closed kinematic chains, which means that the system has, in fact, 2 degrees of freedom, despite having 4 linkages. So we can compute, for instance, the direct kinematics. Where is the end effector located? We can use only the variable Q1 and Q2. So we have, for instance, for the x coordinate, L1, C1, so the link length of the link 1, cosine of Q1, plus only the extra part L5 of the 4th body, and cosine of Q2 minus pi. If we simplify this trigonometric expression, we have a minus, and then just cosine and sine of Q2. So this is the expression of the direct kinematics, and similarly, we can locate the position of the center of masses using only the 2 variable Q1 and Q2. We have LC1 for the position of the center of mass of link 1, cosine and sine of Q1, and similarly with LC2, now you have this term appearing there, time cosine of Q2 and sine of Q2, and so on. Quite straightforward computation of where are the positions of the center of masses in the XY base coordinate frame. And if we have the position, we can compute also the linear velocities. And this linear velocity will be introduced in the expression of Koenig theorem of the kinetic energy of these links. And similarly, for the angular part, we need to compute the angular velocity of this link, which will be related to Q1 dot and Q2 dot directly. So this is pretty much a matter of straightforward derivation. So we have the 4 velocity of the 4 bodies, and we have also the angular velocity of link 1, which is the same of the angular velocity of link 3. These are scalar notation, so we are using two-dimensional linear vector in the plane for VC, so x and y component, and only, let's say, the scalar component of the total angular velocity vector, which is only directed along the z-axis normal to the plane, so we only write this in a scalar way. So we are using a planar 2D notation. And once we have this, we can compute the kinetic energy of the first link, of the second link, third link, fourth link. You see, this energy-based method, once you have characterized the minimum number of generalized coordinates, is applied straightforward, in a straightforward fashion. So you end up with the total kinetic energy, and from there, you can extract the inertia matrix, as we have done before. And you can immediately see that, of course, the inertia matrix is symmetric. The 2 terms on the diagonal are constant, while the 2 terms off diagonal have a constant factor multiplying the cosine of the difference between the 2 angles Q2 and Q1. So this is kind of a different situation as for a 2R planar robot, so the same degrees of freedom, the same revolute joint nature of the actuated joint. Here there were passive joint in the structure, not actuated, but that moves according to the geometric constraint of the parallelogram. So here we have this strange situation, but not really so strange, the cosine of the difference between 2 angles. So when the cosine is 0, so when these angles are now 90 degrees, those off-diagonal term vanishes, but in fact, the inertia matrix is otherwise a function of the configuration. And in this case, pay attention, apparently it's a function of a configuration of Q1 and Q2, but in fact, when we are doing the difference, we don't care about the 0 definition of Q1. So if we reintroduce a relative angle, we will see that only the internal configuration matters and not the value of the first joint variable with respect to a reference frame, the x-axis, which can be chosen arbitrarily, and only the difference matters, because if you change the frame, the difference between Q2 and Q1 will remain the same. So this just to make sure that we are not doing a mistake here. But what I wanted to point out in this case is that there is a special structural condition which never occurs in a planar 2R serial manipulator, that you can render the inertia matrix both diagonal and constant. In fact, if you choose this distribution of masses and of center of masses, so the product of M3, L2, LC3 is equal to the product of M4, L1, LC4. L1 and L2 are kinematic parameter, are the length of this link constituting the parallelogram. So this can be chosen once for all, but then the mass and the center of masses are such that this equality holds, then the off-diagonal term vanishes. The diagonal terms are already constant, so the matrix is not only diagonal but also constant. And the constancy of inertia matrix implies that there will be no Coriolis and centrifugal terms, so C of QQ dot is identically 0. We are moving on a horizontal plane, so the potential energy is constant, its gradient is 0, so the models becomes very simple. It's a linear model for each joint motion, and also decoupled. So there's a M11 and M22, which are those elements on the diagonals. They are constant. So you can not only have no inertial coupling, no Coriolis and gravitational effects, so the models become very easy, but the additional property is that you have decoupling here. So that if you are concerned with the motion of Q1 and you want to design a command U1, both in feed-forward or in feedback, then you don't care what the second joint is doing. You have perfect decoupling, and vice versa. This is a very nice property. Now I'm coming back to the fact that this robot has a direct drive actuation. So the torque, generalized torque, performing work on Q1 and Q2 are the same generated by the motors on their output axis. There's no reduction ratio. In general, if this were the case for let's say a 2R planar serial manipulators, this inertia would be function of the configuration. So when I'm designing a controller for U1 and U2, first of all, I need to take into account the coupling, and second, also the time-varying nature of the inertia because of the changing of the configuration. In this case, this is does not occur, so you can have a decoupled design on a linear dynamics. So you can use, let's say, standard control techniques. Okay, so the fact that this is the case allows you also to have direct drive actuation that have the advantage of not including, for instance, friction and backlash, because there's a direct coupling. There's no backlash between gears. There's no friction due to the contact of mechanical parts. We'll see what happens when we include friction in the dynamic model. So this is very convenient, okay? And this comes together with this mechanical design for the kinematic structure. So what happens when you move this parallelogram on a vertical plane? Then you have to consider also potential energy, which is configuration dependent. You can compute the height of the different center of masses, give an expression for the potential energy due to gravity, exactly like in the serial case, but just adding the correct contribution of each individual link, and you sum the four contribution, you have a total potential energy, you take the gradient, transpose this partial derivative with respect to Q, and you obtain this expression. Now, without any assumption, nor on the inertia matrix, neither on this coefficient, we can immediately see that there's a nonlinear dependence on Q, but this is decoupled. So the first component of the gravity vector depends only on Q1, and the second only on Q2. So even if we don't cancel this out, we will have a problem as before. If we have the previous structural condition on the inertia matrix true, so we have a decoupled and constant inertia matrix, without any additional condition, we have one now nonlinear equation because of this cosine in the gravity terms, but still local. So we can design, for instance, a control loop which works fine here without caring about what the second joint is doing, and vice versa. There's no coupling, neither at the inertial level nor at the gravity level. And of course, if we look at this coefficient, we may specify additional, we have still mechanical design degrees of freedom to zero out this constant, just like we did, for instance, with the A2 parameter in the 2R planar serial case, so that the gravity terms vanishes, and we have, again, under gravity, a full balanced situation. And this is what was done for the Minnesota arm, the spatial one, and can be done also for this MIT 2 degrees of freedom direct drive closed kinematic chain robot when we would place it on a vertical plane. Okay, so this was an extension. So conclusion, we can also use the Euler-Lagrange dynamic modeling approach also for closed kinematic chains, provided that we are able to identify independent generalized coordinate. And this will be the number of degrees of freedom. Despite the number of links, despite the number of joints, some of them are passive because needs to be accommodate the motion. If those passive joints in the structure, so let me go back for a moment to this situation. So here we have two motors on this joint, one that moves the link 1 and the other that moves the link 2. This joint is passive, the green joint there is passive, even this blue joint there is passive. If we would add motors there, we don't increase the capability of the mobility of this system. The system still remains with 2 degrees of freedom. But, of course, we have more torque available. We have a redundancy of torque for moving the end effector, for compensating forces applied or to be applied by the end effector on the environment and so on. We have a case of redundant actuation. We have already commented this in the first simple case of dynamics of the actuated pendulum that we have considered in the introductory part. Okay, so going back to the general case, this we can apply the Euler-Lagrange formalism. We can identify the minimum number of generalized coordinates. This is not always easy. Sometimes you use more coordinates, but you have to impose closure loop, geometric loop on the structure, which will eliminate some of this variable, and then you remain with the minimum number of generalized coordinates, which I remind you should be independent quantity. So quantity that you can move one independent of the other, which is the case in this situation. Okay, so with this in mind, let's move to further extension of the modeling or specification of some aspect. For instance, so far, we have always said that on the right-hand side of the dynamic equation, there will be non-conservative forces. Then, most of the time, we have not said anything more. In the initial example of the actuated pendulum, we modeled some viscous friction. But in fact, there are many sources of dissipating energy because of friction. Okay, so let's, here I'm listing a number of phenomena which dissipate energy, and so this should be terms which appear on the right-hand side of the dynamic equation of the Euler-Lagrange model, so on the U side. Viscous terms are pretty simple, and they consist in torque which opposes motion in a proportional way to the speed of the joint. While Coulomb friction are constant torque which oppose motion depending only on the sign of the speed. So they are not present at zero speed, but they oppose with a constant torque if I'm moving positively, so I'm rotating counterclockwise with the joint, or if I'm rotating clockwise and we have an opposition as well. There are other phenomena. Stiction. Stiction is an extra torque that we need to overcome at zero speed in order to put the system in motion. So if I have a stiction of, let's say, 1 Newton meter on a certain joint, and I'm applying with a motor less than 1 Newton meter, nothing happens. I will remain stuck in that position. As soon as I overcome 1 Newton meter, then the joint will start moving, and the extra torque that I have, let's say 1.1 Newton meter, will all available for accelerating the system, because as soon as I move out of the zero velocity situation, this stiction effect is gone. There are other effects, Strebeck effect. There's many interesting models. There's a so-called Lou-Gray. Lou-Gray stands for Lund and Grenoble, the two universities to which the researcher belonged who developed this model, which generates friction force not only based on, let's say, the position and velocity of the joint, but also on some internal story. So there's a dynamic model which includes a state, an internal state of contact in the joint, which gives an output, a friction torque output with this model. So it's a very more complex situation. In any case, the interesting fact is that all these effects are local to the joints, let's say, where you have actuation. They are not coupled between one joint and the other, like in the inertial case, like in the Coriolis and centrifugal and gravity terms. They are purely local. And they are quite difficult to model and also to identify, because these models contain parameters. You may use a black box, a neural network, to model a friction term, and then train this network in such a way that it reproduces the actual opposing friction that is present in your robot. There are a few exceptions where the modeling is easier, and this is why I'm listing some explicit equation. For the viscous, the red term, the viscous term, as I said, is local, so this is joint I, depends on the velocity, opposes the actual velocity with a viscous friction coefficient, which I call here F. F stands for friction, the subscript V for viscous, and the I for the fact that this coefficient applies to the ith joint. And similarly, the Coulomb friction, again, the blue box, the C stands for Coulomb. And again, the intensity of the speed is not relevant, just the sign. So if I have a positive velocity at joint I will have minus FCI torque on the right-hand side of the equation, so which uses up some of the torque that you're applying and which produces positive energy increment on joint I. The other requires some harder modeling. Here I have added a plot that shows without the minus sign. So it's like if I'm bringing this to the other side of the equation, of the dynamic equation. This yellow line is the viscous friction. Of course, it goes to zero. So when I'm at zero velocity, there's no dissipation due to viscous friction. If the coefficient of friction is higher, then this line will have a higher slope, and so on. The light blue line is the, sorry, this should be sine, not sin. Should be equal to that. I will make this correction on the slide. So the sign of the velocity, so if the velocity is positive, I will have a constant force Fc. So the larger Fc, the larger will be this opposing torque. Of course, this has a plus sign because it's like bringing this term to the other side. Okay? And similarly, what is missing here, what I've not written any equation, is the stiction, or let's say a smooth approximation to the stiction effect, which is always zero and then has a peak here at 0 velocity, and then should go instantaneously to 0. Then we have added some Strebeck effect, so this discontinuity is not there. There's a smooth, although very fast, change of this effect going to 0 as soon as you start moving, but it's still present with some contribution at low speed, in this low speed regime. If you add all this effect, you have this violet curve. This slope is depending on the viscous term. The fact that the slope does not go through 0 is because of the Coulomb friction, and the fact that close to 0 you will have a peak is due to the Sticktion effect. So when you have a combined terms, you have all this together. And you can imagine that this may affect the dynamics in a relevant way. Of course, lubrication and temperature will typically change the value of this constant, which are no longer constant. They are changing, but not with the state of the system, but with some operating condition. How long are you working with the robot? If you're lubricating regularly the joints and so on. So the mechanical part. Another interesting addition involves the presence of motors, of actuators. And let's consider, like in most of the cases, for a small to medium size industrial manipulators, the case of electrical actuators. Now we have seen that the motor is made of an electrical motor of a static part, the stator, which does not move, which has its own mass, and the rotating part, the rotor, which has also an extra mass. In fact, the rotating part, we have made an assumption, which is a design assumption, which needs to be satisfied, otherwise the motor will not last long, that the center of mass of the rotor is on the rotating axis of the motor itself. So what matters in that case for the angular speed is the inertia of the rotor around its spinning axis. So in any case, these motors are additional bodies. And if we are modeling also the presence of the motors, and we should do this in practice, if we are not looking only at the mechanical part, we are looking also at the electromechanical part of the model, in a sense. These are additional rigid bodies, and they have their own kinetic energy and potential energy. So we should add other terms. If we are assuming that these motors are rigidly connected through a transmission and reduction element to the driven link, then we don't need to introduce extra variable. You may remember when we started with the actuated pendulum, we have introduced an angular position for the motor side and then for the link side, and then we have related the two and extracted only one generalized coordinate for that actuated joint. So what can we say in a more general setting? First of all, that these motors are typically placed on the previous link. So they move the joint which is following the link I-1, the motor I. And they are placed either on link I-1 or even before, and probably we will have some transmission element that moves, relocates the motion on the motor axis to the joint axis. But the main assumption is that these motors are mounted before the joint. So motor I that moves joint I, and therefore link I, is mounted on link I-1 or before. For instance, this is the Unimation Puma family. This is the first motor, is mounted on the fixed base, so on link 0, and moves joint 1. There's some toothed gear that transfer the axis, the rotation on the axis of the motor to the rotation of the joint. So this is motor 1 mounted on link 0, moving joint 1 and therefore link 1. So it satisfies this. This is another situation still in the Puma family. This is the Puma 260 of the Unimation. This is the 560. It was the first full Revolut 6 degrees of freedom manipulator built. So this is a motor which is located on, let's say, link 0, link 1, link 2, and is moving joint 3 through an axis, some transmission, and then motion of joint 3 here. And even more, in link 3, we have the 3 motors that move joint 4, 5, and 6, the spherical wrist, and they are placed somewhere here. So always before where the joint is located and the link, associated link. However, there are some few exceptions. For instance, here, this second motor, there's a second motor even here, is the motor mounted on link 2 and moving joint 2. So it's like mounted on the joints and rotating the joint in this way, not before. But this is a very, very seldom situation. So this is a few exceptions that I would like to mention in any case. So we will assume that the first is true. And moreover, in most of the cases, there are also situations where the motor is placed exactly on the joint axis. For instance, in this Mitsubishi 6 degree of freedom arm, this is joint 2, joint 1 is here, the motor is somewhere here, placed on the side, but moving joint 1. Then on link 1, you have motor 2 exactly on the axis of joint 2, and on link 2, you have motor 3 moving joint 3, and with this axis exactly on this joint axis. So still satisfying this assumption that I said before. So what do we have to consider for this modeling? The mass of the motor. But if the motor is not moving, this mass is part of the link to which it pertains. So we just need to add more mass to the link. Of course, the total inertia will change of that link. The center of mass of the link will change. But it's useful to separate the two contributions if needed. So the presence of a mass, of a still mass of the motor, does not change really the structure of the system. And then there's inertia. When the motors start moving, the mass remains at the same position because the mass is on the axis of motion, so the position of the center of mass of the rotor is not relevant, but the inertia, when the rotor is spinning, introduces some kinetic energy with angular motion times the inertia, so an angular part of the kinetic energy. In adding this contribution, we should take into account the presence of reduction gear, often quite large, except for direct drive arms, as we have just commented. And finally, I'm not reading this, but it's not difficult to consider also this. Many cases you have not a one-to-one coupling between motors and driven links through the joints, but you have, for instance, two motors cooperating in moving two joints at the same time. And so you have a transmission coupling matrix, not just a reduction ratio on the diagonal of a coupling of the transmission matrix, but you have a full or locally full coupling matrix gamma with off-diagonal elements. And you can consider this in the modeling as well on the right-hand side between the produced torque by the motor on their own axis and the actual torque that are, remember, doing work on the generalized coordinate that you're using, typically the link coordinates. Okay, so this is a global picture of this situation. We have a fixed zero link with a word frame. There's a frame also at the base of the joint with a Z0 axis on joint 1. The motor is placed on link 0, and then you have link 1, you have joint 2, you have a reference frame of the Denavit-Artenberg type, which is associated to link 1, but has the zeta 1 axis on joint 2, and so on. And you may have, typically, if we are assuming that the motor is placed on the same joint axis, is moving together with link 1, and its motor axis is aligned with joint 2, and so on and so on. You may have this situation or not, but for the purpose of illustration, we are assuming this. Now, you can introduce, of course, link variable. Here we are assuming that all the joints are revolute, so we have a theta variable, and also motor variable, theta m. So we will have a spinning speed of motor 1, which is theta dot m1, and which is connected to the velocity of the first joint, theta 1, and we have this relation because we have a reduction element connected to the motor. And similarly, because of the principle of virtual work, we have an amplification of the motor torque produced from the motor side to the link side of the transmission. And this is the general picture under the assumption that we made before. So now the nice thing about Euler-Lagrange is that we are energy-based, energies sum up, so we sum other terms. And we make here a simplification, a very common simplification, which is particularly relevant when we are using large reduction ratio. So we are assuming that the major part of the kinetic, of the angular part of the kinetic energy of the motors is due to the speed of the motor itself. The fact that this rotor mounted on some joint has an angular velocity because the previous link is rotating is neglected. And only when it starts rotating and it has its own speed, theta dot m of I, then this contributes in a non-negligible way to the total kinetic energy. So we are writing the kinetic energy of motor I just because of its spinning at the speed theta dot mi. So with its own inertia on the motor axis, 1/2 the motor inertia times the square of the rotating speed. Since we have to rewrite everything in terms of the Q's variable, so the generalized coordinate that we're using for describing the link, the robot dynamics from the link side, then we have to scale by nr square, the theta m dot, so the velocity is nr square, sorry, the velocity is nr times the link velocity. Since it's square, we have a square there, and we baptize the product of the inertia of the motors times the square of the reduction ratio. Remember, the reduction ratio is larger than 1. It could be 60, 40, 100, 160 if you're using harmonic drives, so very large with high efficiency. Whatever it is, this value, we baptize this as Bm, so the inertia of the motor, of the rotor of the motor reflected through the reduction ratio. And then if we sum all this motor kinetic energy, we have an expression, a quadratic form in the Q dot with a constant inertia matrix Bm, which is diagonal because of the way in which we are summing up terms and neglecting minor contribution, especially when the reduction ratio is large. So if now we include all this contribution to the kinetic energy, and we include also the previous dissipation effect that we have considered, we end up with such an equation. So we had m of q, q double dot. We have a diagonal addition to the inertia matrix, just because we add this to the total inertia, to the total kinetic energy of the system. The fact that this is constant, so we have modified the original link inertia, let's say, of the robot, the total robot inertia, with a constant term. The constant term will have no effect, like any other constant term in the original M of Q matrix, on the Coriolis and centrifugal term, because these are computed by partial derivative of the element. If you have additional constant term, you will have no contribution. Indeed, there are extra contribution here because of the masses of the motors, but those masses have been included in the link masses, so they eventually appear here. Same story inside the gravity term, so this modification are because of the mass of the motor that you may add. We had the non-conservative forces performing work on the Q's on the left-hand side. If we include, for instance, viscous and Coulomb friction, we had a minus sign there that we moved on the other side, so we have a plus sign, and those matrices are diagonal and positive, because we have a local effect, much similarly to the local effect of adding inertia of the motor. What is left on the right-hand side are the torque produced by the motor, so the actuation torques, but pay attention, not the tau m, but those reflected, so amplified by a factor n of r for each joint, n of r I, to become motors, to become torques generated by motors, but reflected through the reduction ratio. So this is the full model. So we have added extra term. Let us conclude now by this part of the lecture by saying that or maybe we can have still few slides. So by saying that you can, of course, reduce everything not on the link side, but at the motor side, as we did originally with the actuated pendulum. So how do we do this? We have to scale by the reduction gear all the torques present. Remember that if this is a model of a purely revolute joint robot, all contribution have the dimension of torque. So we have torques here, friction torques here, gravity torques here, Coriolis and centrifugal torques here, inertial torques here. So we scale these torques as seen from the motor side. So we scale each equation by NRI, the reduction ratio. So if we work at the vector level, this tau becomes tau m, the motor torques generated by the motor on their axis, so before the reduction ratio. All these terms are scaled by NRI. So we have all these terms here are scaled by NRI, so it's a diagonal matrix. These are collected in a generic vector f of q dot. The inertial parts are treated a bit similar, a bit simpler. So here we have the scaling. Of course, this should be scaled as well, but here it's not relevant. I'm just looking at the scale by a factor, let's say 100, of all these nonlinear coupling and nonlinear terms. On the inertia matrix, we have a special situation. So if we scale by NR, and then we use, in fact, the motor equation, then we have to scale by NR square. So there are two contributions, one coming from here, but if we scale by NR square, we obtain exactly the motor acceleration. And this is the term EM with a constant term. On the diagonal, like this, all non-diagonal terms have been moved inside here. And here I have used the dyadic expansion. These are the columns of the inertia matrix. What remains when I've taken out the inertia of the motor and the diagonal element. The diagonal element are scaled by NR once because I scaled all the equation by NR, and then another time because I'm using motor acceleration rather than link acceleration. So I have the diagonal elements which is scaled by NR square. So at this stage, this considerations, nothing changes, just changing way of representing the model, but we can conclude that if, and this is typically the case of many industrial robots, if the reduction ratio is very large, all these nonlinear terms are scaled by a factor on I. So let's say 60 or 100. The inertial part is almost diagonal because it has a constant term, and then this is varying with the configuration, but scaled by a factor NR square. So if it was 60, now it's scaled by 3,600, 60 square. So this is varying the inertia, but what the motor sees with this torque are still a nonlinear model, but with a dominant constant part and other terms that looks masked. Okay? So this is why in industrial practice, controllers are designed essentially neglecting all this term and neglecting also this part, or considering a minor part here, and considering only the inertia on the motor side in a decentralized way. If this is not possible because the reduction ratio are not so large, then we have to take into account the full dynamics. And this is why when the reduction ratio is 1, so there's the direct drive coupling, all the dynamics would be seen on the motor side. And for instance, with the closed kinematic chain design, we were able to decouple mechanically the system so that we don't see this nonlinearity and this coupling between joints. The last addition that we will consider is the inclusion of joint elasticity. This occurs in industrial robot whenever you're using transmission elements which are intrinsically compliant. So belts, long shafts, subject to high torques, they tend to have a torsion, and typically harmonic drives. Remember that harmonic drives are reduction element and transmission element online, very compact, so the motor is placed exactly on the joint axis with a large reduction ratio and still enough efficiency, like 100, 160, up to 200 reduction ratio. Now, this introduces flexibility between the actuating motors and the driven links. This has been for a long time considered a parasitic effect that should be discarded by control, trying to avoid the arising of vibration because of this effect and recovering both static and dynamic accuracy in link motion, because eventually are the links that should follow the right trajectory so that the end effector, where performance is being evaluated for an industrial robot, remains good. Performance remains good. However, more recently, let's say in research robots that are now going into market, in fact, compliance in the transmission has been introduced on purpose. Or, let's say, not being handled as a parasitic effect, but trying to take advantage of it. And there are two main reasons for this. One, probably the most important nowadays, is safety. If those robots should be used for human collaboration, so with human, in presence of the human in the workspace, then they should be lightweight and possibly compliant for safety purpose, so that if a collision, an accidental collision occurs, not only you have less kinetic energy because the robot is lightweight, but also the possibility of absorbing some of the energy due to the impact into the transmission. So for safety reasons. But later on in research, people have discovered that introducing compliance, and in particular a new class of actuation which have variable compliance, so the fact that there is some effect which can be controlled autonomously, independently from the motion of the link, then this can be used for energy efficiency. So with the same amount of total torque available at the joint, you may play with motion and compliance so that you accumulate potential energy in the system and release it instantaneously, so that you have this explosive motion and you can guarantee very large performance in terms of energetic and dynamic motion. For instance, you can throw much farther away a ball by variable actuation system rather than through a rigid system with the same amount of torque, because of the interplaying of where you accumulate and release internal energy. So in any case, This is realized by introducing compliant elements, for instance, cables and pulleys, or harmonic drives, or also in some system where you have a macro-mini actuation, the macro part and the, let's say, low-frequency part of motion is devoted to the motor, which are macro, and then you have mini motors coupled elastically that achieve performance reducing or eliminating vibration and introducing compliance in the system. There are many different designs. We are not really interested in this. But in all cases, both at the industrial level and in all this research robot, flexibility can be modeled as concentrated at the joint. This is a very strong assumption, but quite realistic. Of course, you may have very lightweight link design, which tends to deform in a distributed way, and this is a completely different story. Now we are considering flexibility only concentrated at the joint, and typically using small, assuming that joint deformation are small, so that we can live inside an elastic domain. This is particularly true in this case when we have harmonic drives. Sometimes you cannot have elastic domain situation for variable compliance systems, so you have to take into account nonlinear flexibility. But in our case, we have, so this is the situation that can be modeled in this assumption. Here you see a robot, an 8R robot developed by Scienza Macchinale in Pisa. We used to have this in our old lab. It's an 8 degree of freedom robot with cable and pulleys transmission. So the motors are placed at the base or in this link, and all the rest of the structure is very lightweight. But the presence of this cable introduces elasticity between the actuation motion and the moving links, the moved links. Same story when you're using harmonic drives. This is the known, we have seen this picture before, explosion of a single generic joint of the lightweight robot by DLR, which became then the AIVA robot by KUKA. And here you have let's say a sketch of a design developed in Stanford, where you have a large motor that at low frequency produced the large part of the motion, and small motors coupled through elasticity, which compensate for vibration. And you have this type of distributed actuation. Now, what happens when you have an elastic joint? I think that the most simple case to understand the dynamics is this academic example. This is a Quanser flexible joint. Is a device built for experimentation, where you have a linear joint with a motor that moves along this linear support, and you have a load which is passive, which is coupled through some elastic transmission with an elastic spring which has a stiffness K. So you're moving only this part, and this mat should follow. If this stiffness was very large, so if K goes to infinity, so this transmission is rigid, then the motion of the motor will be equal to the motion of the link. Instead, there will be some oscillation. And this video shows the typical behavior of such linear flexible joint. So this is the load, in fact, that is oscillating, because the motor that you will see in a moment is oscillating as well. But you see that the compression and dilation of the spring, expansion of the spring, is clearly visible. And also the fact that the two system moves in counter phase, in a sense. And if you have to do a rest-to-rest maneuver without feeding back the oscillation and the actual position of the load, you will have a system which behaves much worse than if you're using full state feedback in order to do rest-to-rest maneuver. And still, these are just rest-to-rest. If you want to follow a trajectory, you have to comply with the flexibility of the transmission. And this opens the problem to many issues from the control point of view, but certainly the starting point should be to have a good model of this phenomena. So if we move from a single, very simple elastic transmission to the case of multi-link robots with elasticity at the joints, we should have a good model to start with as well. So what should we do? In general, if we assume that all joints are elastic, this may not be the case, but just for simplicity of notation, we assume that all joints are elastic. So we have to introduce separately a coordinate for the motor position and a coordinate for the link position that are no longer connected by an algebraic relation. They are dynamically coupled through the presence of elasticity. So the presence of additional potential energy related to the fact that the transmission is being compressed or extended. So if we have an n-jointed robot with elastic joints, we need n coordinates for the link position and n coordinates, so we are doubling the number of generalized coordinates for the motor position. And because of the nice idea of having quantities that have similar dynamic behavior, instead of using the motor position, we use the motor position as reflected through the transmission ratio, but at this point, still in the need of including elasticity. So this was exactly the same operation that we did when the transmission was rigid, but now we will see that there is a displacement. This is why we need to double the number of generalized coordinates. Now, if we compute the kinetic energy of the motor, now we have a different situation as before. So the link are treated as before. Now we have seen that if the transmission is rigid, we can add the kinetic energy of the motor using the same generalized coordinate of the link. Now we have to stick with the coordinates of the motor or of the motor as reflected through the transmission ratio. So for the kinetic energy, under the same assumption of neglecting some, let's say, effect that are minor, so just considering the spinning of the motor as the main source of the angular kinetic energy of the motor. So we start with the same expression as before. We reflect them through the reduction ratio. But now we don't replace theta I dot with q I dot because these are in fact different quantities. Like theta is different from q, so the position of the motor before the elasticity is different from the position of the link after elasticity, we stop here. And when we sum all this up, we end up with a diagonal inertia matrix, but now multiplying theta dot in a quadratic form and not q dot. This is one step. The second step is that we need to add another form of energy. We have kinetic energy of the motors and of the links. We have potential energy on the links due to the gravity. We consider that motors are balanced, so their potential energy due to gravity is constant. That does not depend on the configuration. But there is another form of potential energy due to the elasticity. Again, is only position dependent, so it's a potential energy. And in the assumption that we have small deformation, so in the linear domain of elasticity, the potential energy of a compressed or extended joint, elastic joint, is 1/2 the stiffness of that transmission, elastic transmission, times the difference between the position of the link and the position of the motor as reflected through the transmission ratio. These two quantities are not equal because K is finite and not infinite. So in case of infinite stiffness, we have the rigid case as we have considered before. Now, this quantity has been labeled as theta I. So this is the contribution, extra contribution of the potential energy due to elasticity because of the elastic joint. If we sum them up, these are local contributions, so you can imagine that you have this quadratic form in the deformations with a K which is diagonal and contains the stiffness of the various joints. Now you have everything you need. you have the q's, you have the thetas. With the q's, you have computed the kinetic energy of the links in the quadratic form T of q. Then you have with the thetas, you have computed also the kinetic energy of the motor. You have the potential energy of the links, U of G, due to gravity, and you have the extra potential energy due to elasticity. Now you apply the Euler-Lagrange equation as before, but taking into account that you don't have only Q and theta as, you don't have only Q as generalized coordinate, but the generalized coordinates are determined by Q and theta. So you have to write down 2n second-order differential equation by applying the Euler-Lagrange equation of motion. And the result is quite simple. You end up with a set of equations which are pretty much similar to the case of pure link, no elasticity. But the new term coming from the partial derivative of this with respect to the q is given by this. And on this side, you have a 0. Why? Because you have no direct actuation on the link side. Now that you have separated links from motor by an elastic element, your actuation occurs only on the motor side. Okay? Now, when you're doing the same derivation for the theta variable, since the inertia of the motors is constant, you will not have contribution to the Coriolis and centrifugal terms in this second set of equation. You will now have effect of gravity on the motors. What is left is the gradient of the potential energy to the elasticity with respect to theta. And this will be the same terms of this, but opposite, because once you're differentiating on the top equation with respect to q, and once with respect to theta, so you have the opposite sign. And on the right-hand side, you have the motor torque performing work on the theta. Now, pay attention. If you adds up these two sets of equations, and you assume that k goes to infinity, while theta goes to q, so that you have a stiffer and stiffer joint, so that the motor position reflected through the reduction ratio becomes equal to the link position. So you have this going to infinity, this going to 0, so this is an indefinite product, but in fact this will be exactly equal to the finite transmission torque that you transmit through the rigid joint. Then theta double dot will become q double dot, and in summing this term disappear, the tau will come to the right place, and this Bm will be added to the inertia matrix of the robot links, so that you recover exactly the previous model. If k is instead finite, then you need to work with two different sets of equations. One special situation is that this torque is not collocated with the differential equation that describes the motion of the link. That is the output that you would like to control. And this is a nice problem that has been solved by advanced control techniques. So I think that we can stop here now.